Lecture 11, Cross-sections. A cross-section is a graphic representation of the intersection of the geological bodies in the subsurface with a vertical plane of a given orientation. A cross-section is an interpretation of the rocks and structures in depth, consistent with the information available on the surface and the subsurface. It can also represent the extension of the rocks that have been eroded above the ground. To construct a cross-section, we need to 1. Choose the orientation of the section, this is called the line of section. 2. Construct the intersection of the section with the topography, this is called the topographic profile. 3. Place the surface and subsurface data on the section. These data are geologic contacts and dips on the surface, wells, and depth-converted seismic. And 4. Extrapolate the contacts from the data points to fill in the space below and above the ground. The choice of the line of section is very important. This is a structure map of the top of a sandstone unit. The black lines with numbers are structure contours. Numbers are elevation and therefore more negative values are deeper contours. The color lines are the lines of section A to E. Now the question is, which section displays the true geometry of this surface? You have 5 seconds to answer this. If you answered line of section A, you are right. This is because this line of section is perpendicular to the structure contours and is along the dip direction. If you answer line of section A, that is correct. Line of section A displays the true geometry of the sandstone top. Line of section E is the worst choice, because it displays the sandstone top horizontal. This is because this line of section is parallel to the structure contours and the strike of the horizon. Let's look at how to construct a cross-section. The upper figure is a topographic map with a sandstone layer in orange. The line of section is A, B. The figure below is the template of the cross-section. The vertical axis in the template is elevation, and the horizontal axis is distance along the line of section. The first thing we need to do is to transfer to the section the topographic elevations and the contacts along the line of section. To do this, we can place a paper strip along the line of section as indicated in the figure. We can then mark on the paper strip the topographic contours with elevation values. We can also mark on the paper strip the geologic contacts, here in orange. We then move the paper strip to the base of the cross-section and transfer the topographic contours. Each topographic contour falls at the corresponding elevation in the cross-section. By joining the dots, we reconstruct the topographic profile. We then transfer the geologic contacts to the topographic profile. The orange band along the topographic profile is the outcrop of the sandstone. On the map, we can trace structure contours to one of the contacts. For example, the western contact. These contours intersect the section at the same elevations. Notice that we can do this directly from the map to the cross-section, because the cross-section is perpendicular to the structure contours and the strike of the sandstone. Using these intersections, we can draw the top of the sandstone in the cross-section. Also, using the contact of the base of the sandstone on the topographic profile, we can draw this horizon parallel to the top. At this point, we have completed the cross-section. What if we just have information about geologic contacts and dips along the topographic profile? How do we fill the space above and below the ground? A first guess would be to trace lines parallel to the dips, but this doesn't work because the units intersect. We don't want that. It is actually better to draw perpendiculars to the dips, and along these perpendiculars draw equally spaced marks. We can then follow these marks to trace the contacts between the units. Notice that each unit has approximately the same thickness across the section. This is a reasonable interpretation. In sedimentary basins, rock units often exhibit constant thickness across folds. Another way to construct a cross-section is using the busk method. Here is one example. The ticks in the section are dips. Let's start at the location X, which is a dip measured in a well. First, we trace perpendiculars to the dips at the location X and the next dip to the east. Then, placing a compass at the intersection of the perpendiculars, we trace a circular arc between the perpendiculars. This is the trace of the horizon. We can do this for the next dip to the east. And the next one. The next one. And the last one. We can then move to the first dip west of the well. Notice that in this case, the two perpendiculars are parallel, therefore the horizon in this segment is straight and parallel to the dip. We move to the next dip to the west. And the next one. The next one. And the last one. We have completed the trace of the horizon across the section. We can do the same for other horizons above or below the blue one. Notice that this method preserves the thickness of the units across the folds. For the red horizon, there is a problem at the crest of the anticline east of the well. Here there may be local thickness changes or another structure may be present. Another method to construct cross-sections is the kink method. Here is one example. The dashed lines are geologic contacts, and the ticks 1 to 3 are dips. In this case, we trace parallels to the dips. We start at contacts X and Y. X dips as dip 2, and Y dips as dip 3. We then trace the bisector of dips 2 and 3. This bisector is the limit of these two dip domains. We trace contact Y parallel to dip 3 to the east, and contact Z parallel to dip 3 in the east, and to dip 2 in the west. We then trace contact W, parallel to dip 1. And draw the bisector between dips 1 and 2. Using that bisector, we can complete the western part of the section. Notice that the bisectors of dips 1 and 2, and dips 2 and 3, intersect. What should we do at this intersection? The solution is simple, we just trace another bisector between these two bisectors. This is the bisector between dips 1 and 3. We can then draw the anticline at depth. Notice that this method also conserves the thickness of the units across the fold. So far we have looked at sections where the horizontal scale is equal to the vertical scale, but what if this is not the case? The degree of exaggeration in the vertical direction of a cross-section is called the vertical exaggeration. The vertical exaggeration, V, is defined as the ratio of the lengths of a unit distance on the vertical and horizontal scales, LV and LH, respectively. The vertical exaggeration influences the dip and thickness displayed on a cross-section. Figure A shows the effect of vertical exaggeration on dip. The tangent of the exaggerated dip, delta prime, is equal to the vertical exaggeration V, times the tangent of the true dip, delta. Figure B shows the effect of vertical exaggeration on thickness. The ratio of the exaggerated and non-exaggerated thickness, T prime over T, is equal to the sine of the exaggerated dip over the sine of the true dip. These two equations are plotted here. The graph to the left shows the exaggerated dip as function of the true dip, for various values of vertical exaggeration. A 10 degrees dip will display as a 20 degrees dip on a section with vertical exaggeration too. Notice that the effect of vertical exaggeration on dip decreases with the amount of dip. The graph to the right shows the normalized exaggerated thickness as function of the true dip, for various values of vertical exaggeration. The thickness of a 10 degrees dip layer is exaggerated about twice on a section with a vertical exaggeration of 2. Notice that the effect of vertical exaggeration on thickness decreases with the amount of dip. Vertical exaggeration enhances the difference between gentle, low dip features, such as the unconformity in gentle bed in the section. However, it diminishes the difference in dip between steep features such as the two faults in the section. Vertical exaggeration is great for highlighting subtle stratigraphic relationships, but it is bad for high-angle faults. Vertical exaggeration influences the thickness of gentle layers more than steep layers. For the structure above, in the vertically exaggerated section, the thickness of the layer is highly exaggerated in the horizontal flanks, but it is almost the same in the steep flank. It looks like the layer is thinner in the steep flank, but this is just an artifact produced by vertical exaggeration. Avoid analyzing the geometry of folds in vertically exaggerated sections. Finally, there are two main types of cross-sections. The first one is called a structural cross-section. This is a section that displays the structures as we see them today. It uses an elevation datum such as sea level. This figure is one example. The second type of cross-section is a stratigraphic cross-section. This section displays the structures at the time of deposition of a stratigraphic unit. It uses a stratigraphic boundary as datum, such as a marker horizon or an unconformity. For example, this stratigraphic section depicts the geometry of the subsurface at the time of deposition of the Seneca bentonite unit. Notice that the Seneca bentonite unit has been flattened or restored to its time of deposition. To better understand this topic, please read these sections from Reagan and answer these questions.